Thank you for the invitation. I'm Andrea Bongini, and I'm a PhD student from the University of Florence. And what I'm going to present is a project made in collaboration with the professor Carlo Biagini. And hey, change slide. No, okay. So this research work is part of a broader national project where Professor Carlo Biagini and I are working in collaboration with the technical office of our university and DESCOR, a private enterprise from Rome. This research aims to individuate common standards and protocols which can be used to satisfy the priority action identified by the European Community for the realization of a digital building logbook, which is defined as a common repository for all the relevant building data. In particular, this presentation will be about the development of a solution to link BIM models and existing database thanks to semantic web technologies. All of us know that IFC format, we know IFC format, which is probably the most famous format to share building information among different actors. But someone perhaps doesn't know that this isn't just a file format, but it is a broader data schema, which describes most of the AECO concept from building element, 3D element to 4, 5D object or facility properties. But IFC cannot explain all the knowledge that turn around a single building or a whole project. And in addition, it is complex to manage and modify it. So it has some limitations. They are well known. Especially if we want to talk about digital twin, we need to represent not just the building itself, but also the relationships between it and other information management systems. So also Building Smart, who is the responsible for the development of the IFC data schema, is aware of these gaps, and it has updated its technical roadmap to move from bespoke solution and technologies to solutions that are more scalable and widely adopted, and that can work in a wide range of tools. And between this solution, we can find the concept of linked data, which is the main topic of this presentation. So Building Smart started some years ago with the translation of the IFC schema in the IFC of well ontology. But as some researchers have demonstrated, this is a monolithic ontology. This ontology is called IFC of well, but it is too complex to manage like the original schema. So over the years, a lot of smaller and modular ontologies are born to describe the different semantic domain of a building, and many of them are based on the both ontology, so the building ontology topology. Which is a very simple ontology where main concept as building, site, storage, space, and elements are described. So starting from this ontology, we can expand our knowledge with other vocabularies. For example, we can describe geometry, property status, information about cities, for example, using a Wikidata database, information about damage for historical buildings, or also data collected by IoT devices. So for this research, the methodology followed has been divided in 3 parts. In the first part, the information about buildings managed by the University of Florence have been extracted from the InfoCAD platform, where it's stored and converted in RDF graph via Python script, following the real estate core ontology. Then we have selected one building as case study, where we have displaced some IoT devices, and we have converted the IFC model in another RDF file using, as before, a Python script. And at the end, following the building performance ontology, so another ontology built over the bot ontology, we have described the sensors and the database where the information are stored. And all this information have been finally imported in RDF graph store, which in this case, GraphDB has been selected. So this is a screenshot of how the InfoCAD platform used by the university looks like. It is also the starting point for the first part of the process described before. Inside the platform, we can find information about all the buildings managed by the university until the information about the single rooms. So first of all, the information have been exported in a CSV file and then converted by a Python script in a Turtle file, which is a way of serialization of a graph, of an RDF graph. Then we have uploaded this first graph in our RDF store, and this is a picture of the graph obtained by this first step. So starting from the red circle, for example, which represent Tuscany, we can cross instances like cities, site, building, story, until the single room. And we can find all the static information which were already presented in the platform related to the single entity on the right side. Then we can switch to the second part. We started to model to select some building from the university as case studies, and we have created these BIM models through or CAD to BIM process or scan to BIM process, depending on the initial information. And the ultimate goal was to obtain a model in the IFC format. Here there are some examples of the model made by our group. And so from these buildings, we have selected the Department of Maths, Lissedini, where we have installed some commercial environmental devices that can collect values as temperature, humidity, indoor air quality, sound, and other values. And all these sensors communicate with a central gateway by LoRaWAN technology. Here there is a map of where the sensors have been installed. We have selected the two main rooms of the building, the library, and one of the two auditoriums, so we can have two different kind of spaces. Here we have some pictures of the installation of the sensors in the environment, and the same devices have been placed also in the BIM models in the same location of the real ones, and with an unique code for every devices. So exporting the BIM model in IFC, we have converted this one in another graph, so using also this time a Python script. And we have uploaded this second file in our graph store. So here we have the framework to collect data. So we have these different IoT devices, displays in the building that send the data to the gateway. And from the gateway, the data are sent following the BACnet standard to a server, not managed by us, but by Descore, where is installed the Niagara platform, a proprietary platform, something similar to Node-RED, if you know. And from this platform, we can analyze directly data for creating dashboard, or as we did, we can download all of them in a CSV file and import in another database, like, for example, InfluxDB in this case. At the end, we can visualize data or group of them through other tools like Grafana in order to combine different sources. Why it is? Because we often don't know which parameters use for making queries on different databases because there is not a unique query language. For example, InfluxDB has Flux query language, MongoDB has another query language. So we need some kind of interoperability layer where to look for this information. And on the bottom, we can see the association of the concept of the devices and the data from the database with the building performance ontology classes. Here, a screen from the InfluxDB Data Explorer, where we can make query directly inside the platform, but we want to be more platform independent for this research. So this is a portion of the final graph we obtain where the sensor system is linked to the BIM graph. So I don't know if you can see, but we have different classes represented by different colors, and on the right side we have the static information of the instances. And from this graph we can make queries directly inside the store. So we can use the Sparkle query language, which is one of the unique standard query language that we have developed by the W3C. So we can use it to retrieve information and use the information queried to make other queries inside our platforms, our additional environments. So for example, we have an example of the Sparkle query, and from the results, we can use them to create a flux query inside our Grafana environment. And here we have an example of some custom dashboard that we created in Grafana, where we can visualize the environmental data that we have acquired. So in conclusion, we can say that these standards can help to describe a building and all its different aspects. We don't need to know everything immediately, but our knowledge can grow over time and be stored in different repositories. In fact, this is one of the main points for the creation of a digital building logbook. We don't need to have all the information in one single point of failure, but we can have this information displayed in different sources, in different databases, and different kind of database with different kind of query language. And starting from this data represented in a machine readable way, we can infer new knowledge and use AI techniques and large language model to make reasoning or prediction, because we can start from the knowledge that we can see that we have represented, so the implicit knowledge, to retrieve other sentences, other axioms. Cons, we have an industry that is not ready yet to work with these standards. There aren't commercial applications user-friendly, and some coding skills are still required to implement a knowledge base like this. For example, for the first two phases, we have used Python scripts, but for the third part, for the third graph, we wrote it manually. So we are working on it, and some of our future work will focus on the improvement of the Python script, especially for translating the IFC file in a graph. And we should try the use of R2RML mapping language to map sheets and classes from a relational database in a graph database. And we are trying to implement a Sparkle endpoint, very hard, probably we'll just implement it in localhost because we don't have the permission from our university, but anyway. And we are exploring the integration of a large language model in the process. So thank you for the attention.